We were discussing radio network planning for 2G. Whole thing we're doing as an example of non-LOS communication, which involves the real challenges. And we can see already the frequency chunks are reused at a distance, and there can be potential interference from there. Although we are saying that we'll set it at a good distance, but there will still be some level of interference. Okay. So the system itself is generating interference, uh, and this does not happen in LOS communication. You have a confined area for the propagation of the signal for LOS communication, and you may reuse the same frequency somewhere else, that there is no interference among them. At all the places you reuse, there won't be interference because very confined. Both sides know the location of the other end, and so a point-to-point communication, very narrow beam of antennas you can use. In the case of non-LOS communication, you see for cellular communication, in a cell you don't know where the user may be. Okay, so you have to send the signal in many different directions. So far we are considering only a cell which has a base station at the center. So in that case, you use an omnidirectional antenna radiating equally in all different directions. So you're not confining. Okay, we'll look at now something called sectoring, dividing a cell into 3 or more parts. Okay, 2, 3 or more parts. But even in those cases, the radiation pattern will be quite wide. Because you don't know where the user may be. He is a mobile user, so the base station transmits in many different directions. In the uplink, it is even worse. Anyway, the point is, you have some generation of interference for your own system. Okay, and you can't avoid it. Yeah, I'm now sharing the screen. See, we were discussing this part last time, just showing that there can be interference and how we can calculate the level of interference. Okay, so we are considering this Q, okay, to estimate the interference. Okay, we're saying that we are setting the interference signal at certain good distance, but it is still a source of significant interference. So we have to estimate that, and we have to take necessary measure. Okay, just trying to keep it low, and then our bit rate or data rate will be actually depending on the level of interference. Now, most of the time, the cells are sectorized the way it is shown here. At the center of these cells, there are base stations shown as these red dots. And you see that we have 3 sectors in a cell. The base station will have 3 sets of antennas facing in these three directions. In 2G, I mean, these small parts are called sectors. Okay. We'll look at you see, you have three antennas facing three different directions. Okay. You may have found this way. At the top of the tower, there are three base stations in three different directions. These the number of sectors doesn't have to be three always, but most of the time it is three. It can be two, it can be four, it can be up to six. So you'll actually have to use an antenna which is directional when you use sectoring. It is not omni. Omnidirectional means you have no sectoring. At the center, you just put your base station like this, and the antenna will radiate equally in all different directions. But now, of course, every antenna will cover its own sector only, so it will be directional. However, the radiation pattern will be pretty wide. Radiation pattern, because you don't know where the user is in the cell, or I mean, you actually want to cover all the users in the whole sector. So a wide radiation pattern you have to use. The radiation pattern is 60 to 80 degree wide for three sectoring when you use three sectors horizontally. However, vertically the radiation pattern is pretty narrow. I'll show you why. And it is between 5 to 15 degree typically. Okay, these are not fixed numbers. Okay, uh, and as I said, the number of sectors are also not fixed. These things can vary widely from case to case, and the real life cases can have many different I mean spatial conditions. Okay, so I said that in almost 80% cases there are three sectors, and omni cells are also used to some extent, and sometimes 2 or 4 sector cells are used. Other numbers are very rare. It can be up to 6. Okay, now let's use an example. The operator has a 15 megahertz spectrum from the government. Now it uses n equals to 4. N means the cluster size. You have 4 cells in a cluster. But now we are showing that we also have 3 sectors in every cell. Okay. If we have 3 sectors, then of course the different sectors will also be given different frequency chunks. Okay. We know that all the cells in a cluster are given different frequency chunks. But if you have further sectoring, then every sector in a cell will also get different frequency chunk. So the number of frequency chunks here in this example will be 4 times 3, 12. So we have to split the whole spectrum into 12 parts. You can also think of it this way, that we have 200 kilohertz chunks for use in 2G. So the 15 megahertz spectrum consists of 75 channels. 15 megahertz by 200 kilohertz, 75 channels. So these 75 channels you have to distribute among 12 sectors or among every cluster. So every sector in a cluster will get 6 or 7 channels on average. Okay. So these are pretty common numbers in practical radio planning for 2G. Most commonly N is 4, and most commonly you have 3 sectors. Okay, so these are common practical numbers, and now you see that with 7 channels in a cell, you have 7 times 8, 56 time slots available. So 56 users you can accommodate. However, 2 of them are used for control purposes. So for real data, you use 54 time slots, or 54 users can call at the same time. They have voice slots for voice calls. But just to let you feel that a voice call involves two parties at the two ends. So if both of these parties are in the same cell, then every voice communication setup, okay, is using actually two time slots for the two users at the two ends. So you have 20 okay, 7 calls for the 54 voice users. Okay. Uh, questions? Questions? Okay. Now, in the case of 3G and yeah,
So,
yeah, yeah.
how do you get the 27?
Well, it may be 54. Okay, but I just wanted to let you feel that you have actually two users for every voice call setup. Okay, I mean, two people are talking to them, talking to each other. So both of them requires this type of, if both of them are using 2G services, both of them require time slots. They both consume time slots. Okay. So if you consider this consumption at the same cell, then you have 54 time slots. Okay. To allow the users to access the radio resources. So 54 will be used, and every two will be used for a particular voice call. So 27 voice calls can be set up, right?
Yes.
If you consider, I mean, both users of a voice call in the same cell. Okay, now the uh, figures that you see, sometimes you have them at the rooftop, the antennas, and you may find these 3 sets of antennas at 3 different corners of the roof. Okay, this have to cover 3 different sectors. They face different directions. Okay. And sometimes you'll see a pair of antennas, okay, instead of one. Now I'll discuss why you find a pair instead of one. Here we have just one antenna for every um, sector, but actually it is not a single antenna. I'll show you what we have inside. Maybe we jump there right now. This whole thing is actually a casing. The real antenna is sitting inside. I'll show you how. You see, this is the real antenna. This is the real antenna. Okay, and that you house this way. You have some metallic casing. This is the rear part. You can see the rear part. Okay, so the real antenna is set up in this metallic frames, and they work as reflector. So you don't have any backward radiation. All the backward radiations will be reflected, and this energy will be sent in the forward direction because of reflection. And this whole thing is covered by a transparent uh, thing, and the cover we don't see here. So what you have here is just the cover. Okay. On the at the top of this whole casing, we see the cover. Through that, the signal can easily propagate. And at the rear side or at the two sides, you have some metallic reflectors. Now, let's discuss why we have a pair. We have two at instead of one. Okay, sometimes you may have noticed uh, the base station. A lot of times you have a pair of antennas in every direction. Well, the technique used there is called signal diversity. We know that we have a multipath environment. The signal gets to the receiver via many different paths this way. And because of that, we have continuous fluctuations at the receiving end. Uh, we it would be good if we had a signal analyzer, okay, to show you how the signal keeps fluctuating uh, at any point. So it it keeps fluctuating this way, and different points, okay, will have different types of fluctuations. If we consider two different positions closely apart, actually they are apart by a short distance, but we have two, there will be two different types of fluctuations. Now, won't it be a good technique that we monitor these two receptions? Give me a second, please. I'm sorry, I have got cold and I just wanted to uh, clean my nose. Anyway, uh, you once you have uh, monitoring at two different positions, okay, you will find two different types of fluctuations. And between these two fluctuations, of course, one will have a better signal than the other. Yeah, do you understand anything? uh, do you see the screen? Signal A, signal B.
Yes, sir.
Okay, so these at two different points, A and B. If we keep monitoring the signal, the positions may be closely apart. Okay, but if we watch the receptions, and that we can use actually using a pair of antennas. Okay, instead of just monitoring the reception at a single point, you monitor it at two different points, and then one of them will definitely be better than the other. So always pick the better one. Okay, so that way you can improve your reception to some extent. Okay. Any technique that improves the reception can be useful, and usually the gain is 4 to 6 dB. 6 dB means 4 times power you may receive. Okay, so you may have two receiving antennas instead of one. Okay, so this is called signal diversity. Actually, this technique we are showing is receive diversity. You may have a single antenna. Okay, sometimes they use this way, a single transmitting antenna, but two receiving antennas. Okay, but you won't see this configuration now. Okay, this one I used here just to explain. Okay, I mean nowadays these configurations are not used. What you may, what you see really, like inside the casing, you have multiple antenna elements. Okay, sometimes you have, I mean, you have a single casing, but I mean, on one side you could have two casings. Okay, and that's what you have here. But even that's what you have here, two casings. But even inside the same casing, inside the same casing, you can have actually two different antenna elements. Like you have, oh, I see. So I'm sorry. I'm sorry. The two different casings are probably for two different bands. Okay, but every casing had the signal diversity antenna elements, two antenna elements for the diversity purpose. The two casings are used for the support of two different frequency bands, like 900 and 1800 bands have quite a bit different requirements for the antenna elements, the sizes of the antennas. You know that for higher frequencies, the wavelength is smaller, so the antenna elements will also be smaller. They have array antenna array, a number of elements to implement the same array. So say for if you, you look at the left one, for every antenna array you have three elements. Okay, so this okay, maybe I draw here. See, these three forms one antenna array for reception. Okay, and then at some distance you have another antenna. The antenna has three elements in its array. Okay, and you have these two to implement the receive diversity. Okay, the signal that diversity that we have just explained are used in monitoring the reception at these two antennas, and this may be used for 900 megahertz support, 900 megahertz band support, and for 1800 megahertz band support you need another set of antennas or antenna elements. Okay, like you have here 5 elements in one antenna array. Okay, for 1800, and then you are also using the diversity, and so you have another antenna array. Okay, so this way setting two antennas or at some uh, distance or at different space positions are called space diversity. I mean, it is receive diversity, but this technique is how I get rid of it. is space diversity. So this part is space diversity. However, more commonly people use what is called polarization diversity. Let me delete these things. In the case of polarization diversity, you use two different polarization orientations at the receiving end. Okay. Like it could be horizontal and vertical. The received signal may have different orientations when it gets to the receiver. So at the uh, horizontal, you see you have all vertical elements in the first array. In the second array, all horizontal. So at these two different antennas, you will have different receptions. Again, one of them can be better than the other. So you select the better one. This is called polarization diversity. Okay. So you have one transmitting antenna and then two receiving antennas. Okay. So, but now I'll show what you have most common. Well, another combination is that you use the same antennas for vertical purpose. Okay. The vertical antenna is used for both transmission and reception, and then the horizontal ones are used for reception only. Okay. Now, most commonly, people use what we are showing now and as our last topic of polarization. I mean, polarization diversity or signal diversity. Well, usually your phone is located at some inclination. When you talk or when you use anyway, you hold it in your hand, you put it next to your head, or you hold it at your, for browsing or other purposes. You also hold the phone inclined. So as it is held inclined, it makes sense that from transmitting side, you also use an inclined orientation of your signal. Okay, so the way you transmit from your transmitting end, the polarization orientation should be either vertical or horizontal. Rather, it should be something in between at an inclined position. So you may use 45-degree angle. Okay. For the transmission purpose and also for the reception purpose, you use these two different polarization orientations, plus 45-degree and minus 45-degree. Meaning that here you see these two colors, you can explain. See, the light blue elements form one antenna and the dark blue elements form another antenna. I mean, these are the elements of the antenna array for one set. Light blue elements form another antenna array. So you have plus 45-degree antenna and minus 45-degree antenna together. So you are using polarization diversity. You'll receive at the both antennas and uh, select the better one. Okay. So now this actually forms two antennas. These two elements form one antenna. Okay, we have four segments here, but two of them form one. Okay, I mean, two of them at the two corners and at the same straight line, say at the line with the green one. Okay, you have one antenna element, and the two along the blue line, you have another antenna element. So plus 45 degree and minus 45 degree. And this way you have multiple elements, and then you form the total antenna array. However, the two different sizes you may house in the same casing for the purpose of support of two different bands. Like you could house them in separate casings. Okay, so different. That's why you can see sometimes two different casings. Okay, at the top of the tower, facing in a particular direction. So, like, consider the left two, the antenna array in in one casing support 900 megahertz, and a separate antenna, separate casing houses the antenna arrays for 1800 megahertz. Of course, the higher frequencies will use lower dimensions for your antenna elements. However, you could use a dual band configuration where the two uh, types of antenna elements are put this way. Okay, the large one, then the smaller one, then again the large one. So alternatively, you put them. So this is actually what you have in here: the large one and then the small one. Again, it will be the large. Okay. So we see the antenna this way at the top of the towers. Okay, but inside them you have this kind of configurations. This kind of configurations. Okay. Okay, like you have them this way, and you have plus 45 degree 1800, minus 45 degree 1800, then for 900 also plus 45 900. So this way you need connections to the elements. Okay, and the purpose of combine, I mean, you can combine but that detail we may not discuss. uh, I mean, there are different types of elements that can combine the signal for, I mean, these are called couplers, dividers, okay, which can actually combine or uh, split the signal. Okay. Anyway, here you have another type of orientations for the antenna elements. Okay, finally, we wanna look at a summary of what your design targets are as a radio network planning engineer for cellular network, and what you work with, okay, to uh, reach your target, okay, or to meet your goals. Well, there are actually twofold target: coverage and capacity. And this whole job is called radio network planning, or RNP, and the skilled engineers work very hard for several months to prepare the RNP for the deployment of an operator. First point, they I mean, focus is coverage, where they try to maintain good signal quality at all the points in the area. Okay, or they try to avoid coverage holes. I mean, different some areas have almost no signal. Okay, so people there will not find this. However, this is also um, dependent on the user distribution, okay, and also the type of users that you have in the particular area. Like some areas may not have even any user. Okay, well, there may be a lake or something. Okay, uh, so there may be some areas or some hills. Okay, so some areas you may uh, live without coverage. That is also possible. However, you may want to cover even the lakes. Okay, so when people have a boat journey, they may want to make calls. Okay, so but you don't uh, make sure good coverage or even good capacity there. Okay, so I'll talk about capacity. But the coverage means that the type of the quality of signal, okay, you maintain at different positions in the space or geographical area. Okay, so availability of sufficient signals, and this signal, of course, will be uh, estimated in terms of what you receive from the base stations. So the downlink signals. Af- After RNP, people set up the base stations, but before uh, its a complete rollout, okay, before you make it available with the users, some tests are done, and then you check how the downlink signals are. So you start transmission, but commercial users cannot still access. Rather, the test engineers check how the signal levels are at different user locations. The second point is capacity. How, okay, give me a second. Capacity means how much resources you make available with the users. Okay, the users may require high data rate. So whether or not you have enough radio resources available to meet this demand. Okay, so we discussed uh, with an example that the board budget area may have this many users, but it grows to some other number. So then you have an increased demand for capacity. It's not about coverage. The whole area, board budget area, may have sufficient signal level, but you don't have enough radio resources to ensure that the different users can enjoy enough data rate. Okay, so that uh, is given with how much radio resources you have. Also, it depends on the signal level SINR for the user. Okay, remember the Shannon's capacity. Both SNR and signal bandwidth affect your. Give me a second, please. Sorry. So both SNR and bandwidth affects your data rate. So this bandwidth comes from actually, you see, with our previous example, in the case of 2G, we had certain number of channels available in a cell. Okay, so that is sort of bandwidth. You had 7 channels. So in the whole cell, you had in that example, okay, 7 times 200 kilohertz, so 1.4 megahertz. So that is the radio resource you have. You're sharing it with different users in the cell. But if you had an increased bandwidth, then of course your capacity would be better, and you could provide better data rate. So the first point, coverage, makes sure whether or not you have enough signal quality or enough SNR. The second point indicates how much W bandwidth you have. Okay, so depending on W and SNR, the users will be able to enjoy the data rate. So these set some goals for you to meet, but how you meet these goals? Actually, working with a number of things, and these things have been listed here. They play around with different things like the location of the base station, the number of the base stations, first of all, and where you put them. Okay, the number of sectors, it's up to you how. Okay, you need to consider. They also actually consider where they get the best revenue. Okay, so see the rich people or the corporate people, they use expensive packages, and you need to make sure that they are satisfied. The qualities of service should be good in Gulshan or this kind of areas. Okay, so people have different types of tolerance there. Okay, poor quality service, they won't tolerate, they would switch to another operator. So all these things are actually considered in the case of radio planning. The engineers don't provide the same type of quality everywhere. In rural areas, they don't provide the same type of quality. Okay, because it's all about revenue. It's all about money making. Uh, but the for all these purposes, what you work with, you uh, uh, determine the number of base stations, you determine their possible locations, how many sectors you should use, then the direction for different sectors, which way you face the antenna. It's called azimuth. Azimuth means horizontally, how much angle you make from north. Okay. Then the antenna height, the transmit power for your antennas, antenna gain, okay, or HPBW. And then also something called down tilt. We discussed it's we already actually discussed it. So the antenna will face towards the ground, and you can control. Okay, this control, I mean the angle it will make with the vertical direction is called the down tilt. And this down tilt angle can be adjusted mechanically or electrically. Okay. Both controls are made automatically. I mean, you connect your laptop with the base station and then give some commands, and then it will adjust the angle itself here. This, okay. Also, there can be electrical angles. In that case, you use some antenna arrays. Okay, and the antenna array can have radiation in different direction depending on the phase difference among the antenna array elements. As you feed the signals into the different antenna elements, the phase difference among them dictate which way the antenna would radiate. So the antenna physically may be sitting vertically, but it will radiate to some other direction. Okay, so depending on phase differences of the signal phase. So this is called electrical control of the direction or electrical down tilt. Okay. Like we discussed that the radars keep rotating physically and if we find its rotation, but sometimes it sits idle and with this electrical uh, technique, controlling the phase difference, you actually sweep through a part of the space, okay, in different directions. It radiates, it transmits and receives. Okay, now you see that you actually cover certain area in the space, and that is how you define your cell area. Okay. Next to that, there will be another cell area. So your down tilt decides this. Now, this vertical beam width, you see, won't be too large, because if it is large, then you cover, your cell size is very large. Okay, so it depends on your cell size. It also depends on the height of the antenna, that down tilt. So all these things, the height, the antenna gain, and the antenna gain and the down tilt, they decide, I mean, what the cell size is really. And this, I mean, different parameters allow you to control differently. Like the cell size also depends on the transmit power. So as you lower the transmit power, your cell size will be smaller, because the signal has, sort of dies out at a shorter distance. So the cell size will be smaller. But another way to reduce the cell size can be increasing the down tilt. So instead of, okay, try to get the point. So instead of reducing transmit power, you may keep it at the same level, but increase the down tilt. That way, you have reduced the cell size, but these users, the users in this smaller size, don't reduce their power reception. They have the same high power now. Okay, if you reduce the power level, then the people here within this cell area would also have lower power reception. But now when you increase the down tilt without changing the power level, these guys have no sacrifice in the receive power. Okay, but the cell size has got smaller. Uh, Now, different tools are used for the radio network planning, and actually they also use different simulators, link level simulators, system level simulators, along with these tools. Okay. So I've listed the popular tool names. Okay. From different, the first term in the tool name usually represent the vendor. Okay, not always, but sometimes. Like Thames was primarily built by Ericsson, but later they sold it to somebody, I don't remember. Okay, Thames was the most popular one uh, in the past. Anyway, Atoll was also popular. We have a, I mean, a version of Atoll with some crack. Okay, we'll demonstrate it shortly in one of our experiment. By the way, this week we won't have any experiment. Next week we'll have our next experiment, and that will use the Wi-Fi designer from Cambium Networks. Thereafter, we'll demonstrate atoll. Okay, so these are called RMP tools. Okay. Another set of tools are used for drive test purpose. Like I said that you set up the base station, then you check how the signal levels are. Okay, and the tools you use there are called drive test tools. I mean, people drive through different routes with these tools, and all data are captured. But they don't check only the signal level; they check hundreds of things. Okay, they can see the signals from different base stations around. They can capture the different messages between the phone and the base station. So these tools are like, I mean, you have them installed on your PC, and then your phone can have an interface with the tool using USB port. Okay. Now we purchased Xcal and we'll demonstrate it. Well, actually we'll demonstrate it in the uh, next course. Okay, in the cellular communication course. Okay. Okay, and questions? Uh, Nowadays, Huawei has most of the services in our country. Okay, so Nginx Pro is actually very widely used. Uh, However, there is a set of post-processing tools. The captured data may be further analyzed to find out some graphical representations, or I mean to look at things with some details, or after some post processing. Okay, you find out different results in a more organized way. Okay, the drafted tools can show you everything live. The messages you can look at, you can read. Okay, different things can look at, but the whole data is recorded, and further processing can show different things in a more organized way. Okay. Questions. The Actrix analyzer support most of these drive test tools. Okay. So, I mean, the four post-processing tools are actually from the same vendors. Okay. So, Xscape supports the data recorded from Xcal. Nginx Assistant supports the data captured by Nginx Probe. But Actrix support, I know that it supports Thames, Nemo, and Xcal. But I don't know if it supports or not, whether or not it supports Nginx Probe. Okay. First three, it supports, I know. Okay. Questions? Not, I will. Sorry. Discuss the different path loss models today. We already know what path loss means. When you transmit the signal, as it propagates, it loses some energy. At the receiving end, you receive a lower level of energy. Okay. So the energy that you lose on the way, or different by the loss of the energy on the way doesn't always relate to absorption, okay, or really, energy captured by some other means. Rather, it may be even because the signal is spreading out, okay. Whatever the reason is, it will be referred to as path loss, okay. As long as it it contributes to the difference between the transmitted power and the received power. Okay. Your received power may be 10 watt, and you may be receiving say 1 watt. Okay, then the whole 9 watt will be referred to as path loss. And there can be multiple reasons. There can be say 100 reasons for them. But you don't have to look at the reasons. The the difference that you have between them will be referred to as path loss. However, you need to include the setup and configurations uh, at the at both transmitting and receiving end. You have some setup, and that also contributes to the power that you may receive. That you don't include in path loss, like the antenna gain and this type of things. So if you reduce your antenna gain, you will have lower power reception. Okay, but that you must not account for path loss. So the transmit power antenna gain features, okay, these are separated, and then there'll be different reasons to have some attenuation of signal on the way. So this is path loss. But how the path loss may be in a particular area, very difficult to estimate beforehand, and it has no fixed value. In the same area over time, it keeps changing. But there are a lot of efforts to have a good estimation of a path loss for a particular area, and accordingly you set up your communication setup. Okay, your communication setup will be based on how much power the signal loses on the way. Accordingly, you set up the transmitting end. Okay, how much power you need to send. So you have. We will later discuss something called link budget, where it may work this way, that we need this kind of signal reception at the receiving end, and we'll calculate how much power we lose on the way. Then you can decide, okay, this much power I need to transmit from the transmitting end. It's very important that you transmit at the appropriate power level. It should be barely enough. If it is lower than the optimum level, then the reception of signal will not be good in your cell. On the other hand, if it is higher than the optimum level, then at the cell where you interfere, you know that at a distance you have the use of same frequency. So that's, you are actually interfering that cell. So if you increase your power too much, then you interfere more. So performance will degrade at that cell. Okay. So people try to accurately estimate, but these estimations are always crude. We'll discuss how the, oh, I could show this figure. Sorry. Sorry, I don't know why I didn't show it earlier. So this, you see, we have some loss of signal on the way, and um, link budget is a good way to calculate the power level. Different figures. Okay, with different figures, you try to calculate more accurately. Now, today we'll discuss how we can estimate the path loss on the way, and this path loss refers is also referred to as large scale fading. Okay, I mean it's a it's a contribution from the large scale fading. Earlier we uh, dis- discussed that fading has large scale and small scale types. Okay, so the discussion on fading actually relate uh, address the small scale fading part. Okay, but this path loss model addresses large scale fading. Uh, when you write down some equations to represent the path loss, very commonly we'll be using these notations where the power reception will be shown as a multiplication of P and G. The received power will compute as P and G. In this case, we assume that the receiving antenna has a gain 0 dB, or I mean it's 1. Okay, 1 in ordinary unit and 0 in dB. So the receiving antenna is gain 1. Well, let me tell you why it is considered actually in cellular environment it is very commonly considered 1, because you see from when you transmit from your phone, you don't know which way your base station is. On the base station side, it has certain area of coverage. We showed that the horizontal antenna radiation pattern, radiation beam can be 60 to 80 degree. Okay, the base station knows that these our receivers will be within this area, but your phone may be connected to a base station towards north or east or west. You don't know where the base station is. So your phone actually radiates equal energy in all different directions. So it is an omnidirectional antenna. The phones are always omnidirectional. And also vertically, it has pretty wide angle, because you also don't know how much angle it makes vertically. The phone can be put in any direction. You can have any control on the users, how they hold the phone as they use. So it will make any angle with the base station, even vertically. So both horizontally and vertically, you have to be, you have to relax. Okay. Horizontally, you allow it to radiate equally, so, and vertically also you allow pretty wide angle. Remember that in the case of downlink, the antenna angle was narrow vertically. Okay, so you don't have a coverage beyond yourself. But in the uplink, it will be wide. So the total antenna gain will be very low, very low. And please recall the hypothetical antenna isotropic, where you have equal in, I mean, equal energy in all different directions. Then it is your G is 1 or 0 dB. So the antenna for cellular phone is close to that. Okay, is close to that. So it is just considered 1 or 0 dB. Here we are considering like that for GR. For GT, we are actually, I mean, this P is used to represent EIRP or PTGT. So for us here, P represents PTGT and GR is 1. So, I mean, you actually have PTGT GR, okay, represented by P because GR is 1. Okay. Now, when you I mean, when we discussed this free space equation, we had an equation, in dB form, it was like PT plus GT plus GR minus PL, right? So here you in dB form you can have we are okay, we can consider this way, and PG is uses ordinary units. Okay, so if we consider this PT GT GR together as P, then that PL we need to subtract in dB. Okay, so but if we use ordinary unit, okay, then for minus PL, what do you need to do? For this conversion from dB to ordinary unit conversion, we know that we first divide by 10 and then we put the value as a power of 10. So we subtract PL, so we have minus PL that you divide by 10 and put as the power of 10. This is your G representing path loss. Now this G does not represent antenna gain. It represents the channel gain or the path loss, the multipath channel gain, the path loss. Okay. So you multiply that with P. Okay. P is PTGT. Also in ordinary unit. So you multiply with G. So you have the total receive power in ordinary unit in watt or milliwatt. Okay. Now we will discuss how you can estimate the path loss. There are basically three kinds of path losses. I mean, the analysis can be based on different physical facts or our knowledge, okay, about say diffraction, reflection, and all these things. But it can also be sort of empirical. You measure the received power for a particular area, and then from a number of measurement results, you try to estimate how much signal you lose in this kind of area. Okay, these measurements can give you better understanding for signal losses on the way, because that can include the numerous natural effects. In the nature, many different things are actually affecting. Okay. Reflections, diffractions, a lot of things are affecting this total signal reception. So with our physical analysis, it is difficult to actually incorporate all these things. So measurement results can give you better idea. Well, we're close to, okay, we have just 3 minutes left. Do you have any questions?
No, sir.
Okay. Okay. So the Atlas models have 3 different classes. You use the theories completely. Okay. Like the models we have discussed, free space equation, that itself is a model. Two-ray model. These are deterministic models. I mean, based on theories, we derived a model to calculate our receive power. Okay. And they are, you know, I mean, the difference between the transmission PTGT, GR, and the receive power. Okay, the difference between them is the path loss. So these are deterministic models. But another set of models can be completely empirical models, completely depending on the test results. We discussed recently, there is a model, I mean, there are some tests in Tokyo, okay, and a model was developed called Okumura model. So that is completely empirical model, completely dependent on tests. However, there is a third class which is in between. Just it uses the theoretical model, but the theoretical development is tuned depending on some test results. Okay, so in some cases that can give you more reliable results. It depends on your particular situation, which type of models can be more reliable. Okay, well, just 1 minute left, so we'll discuss a number of models from each of these classes, but these will all only be just to show you the examples. Okay. Okay. Any questions?
No, sir.
Okay.
Sir, one small thing, sir. The maths that you give in the exam and quizzes, sir. Like, sir, we have nowhere to practice them from, sir. So, is there any possibility that you could give us some sources from where we could practice? Because, like yesterday, the maths was a little tricky, sir. Like, you have to link stuffs, but like, if we could just practice, sir. Like, is there any source that you could suggest us?
So the math contains 2
Yes,
marks,
sir.
18 marks also.
Yes, it's like
You know what?
we don't know, sir, like where to practice from. Like we're like relying on your notes and the class lectures, though. So if we could suggest us some sources so that we could practice before the quiz or the exam.
The book of Rappaport has some examples.
Okay, sir.
Couple of examples. Okay. I mean, on trading, they had a couple of examples, and but I also told you that there are. I mean, you could try the questions. Okay, the recent questions, the problems you have in the recent questions. You see, I need to give you something new because it's an open book exam.
Yes,
Okay,
sir.
so
Yes, sir.
if
We
it is,
understand, sir.
so that's the key point here. Okay, the problem, the question I made it like because it's an open book exam. If I need to make sure that there is no cheating. Okay, that question type can help me here.
Yes, sir.
Okay. What else?
Okay. Answer. Is there any possibility that you could like give us an assignment that could be equivalent to a quiz? Like, is there any possibility of having something like that?
See, even in the case of open book exam, it is
Yes, sir.
difficult to actually stop cheating.
Yes.
Okay, so
Because we've
I
seen the
try
books. Yes, sir.
I try with different methods like the type of question,
Yes.
our video monitoring. Okay, so assignment will be a lot more difficult thing. See, I also use the straight numbers in the question. So
Yes.
in the case of assignment, it will be even more difficult. Okay,
Understands. Yes, sir.
right. So that's the key problem. Okay,
Okay.
I mean, you students are so good friends of each other. Okay, so
Yes, sir.
helpful. Yeah,
Assalamualaikum, sir.
so
We have a
helpful in our
class
country.
now.
Yeah.
Can you
Okay.
excuse us?
Yeah. Yeah. Sure. Let's stop here. Okay.
Okay.
Thank you. Thank you for your time.
Oh. But sir,
Assalamualaikum.
if you could, sir, give us an assignment, sir, it would be really helpful, sir.
Okay.
Because like if
Okay.
we
We'll talk
yes.
about it tomorrow.
Okay, sir. Okay, sir. Okay.
Okay.